I'm Brian Peceny. I'm actually your current president of ASPE West Michigan. I've been working in the business for many years, over 30. Primarily started with HVAC. I think a lot of us do a little bit of this, a little bit of that. Plumbing in general and venting even more, I always found kind of a little bit of mystery. I don't know how people on this call have learned venting. I learned from the person that was senior to me. And there are a lot of good publications. And I was, when I was volunteered to give this presentation, I was trying to think what would be the best one. I considered doing some PowerPoints, but frankly, that's rather time consuming. I'm going to recommend what I do. My main source of information for venting is the International Plumbing Code commentary. And for those, I think everyone, I know we have some friends from out of state, but I think we're all Michigan, and those that might be attending are based on the International Plumbing Code. Now, when we talk about plumbing, there aren't a lot of difference between the codes, but the other big one out there is uniform, and there are some differences. And the other great resource is ASPE, and by that I mean, let's see if I even have it on. For those who are unaware, if you're a member, you can get access to all the books. Let's see if I can. Is everyone be able to see my screen? I had right now I'm showing an ASPE page.
We do not see your screen right now.
Oh, I didn't start sharing. That's an issue. In a different space to try not to disturb my neighbors. All right, it seems I believe people can see my screen now.
Yes.
And this is just accessible through ASPE's webpage. If you can get a hold, I like the old books, but they don't offer the books anymore now. It's in access all 4 volumes of ebooks you can download for free. And there are some most benefits. And here's an example. They got the volume 1, 2, 3, 4, and there are other useful guides. The other one that I'd recommend for any engineer that's going to be doing plumbing to consider doing the CPD exam. It was, I took it after being in the business for 30 years, and I certainly learned some new things. It was a good refresher and a little bit more of the engineering behind a lot of what we do. I'm going to try to keep this a half hour. Frankly, you could spend at least a day on venting, and so I probably won't get through it all, and I apologize for that. So what I did is I took the international commentary and I just made a copy, and I tried to edit and highlight things that were, I think, of interest. I'll try to breeze through definitions. The reason I bring definitions up, a lot of us are just do plumbing without even understanding all the elements, because who's read the commentary from all 600 plus pages, or read from cover to cover various plumbing publications that are available. I got branch pipe, again, this is just like any branch, the HVAC, plumbing, domestic venting. It's just a line feeding out to multiple fixtures, usually 2 or more is what we're thinking. It can't be a single. Here's a branch vent, again, a vent that's serving more than one, usually 1 or more individual vents. That's once it starts goes horizontal. Building drain and building sewer, interesting concept. Again, I'm touching a little bit on sanitary, but obviously venting and sanitary go hand in hand. The building drain is that main sewer line or drain line that's under the building. The main connection to sewer is where it connects outside. So we use it interchangeably. I worked in places that we call everything sanitary sewer, and maybe some always call it sanitary, some always use waste, but be careful with that. Sanitary, building drain that conveys sewage only, and you'll see me highlighted. That's different than waste. If people aren't aware, waste is non-fecal matter, no water closets in that. So your normal sinks, hand washing sinks, anything with relatively clean water is considered waste, but it's not sewer, it's not sanitary, it's not soil pipe. So again, here you see the building sewer here, where this is the building drain. And drainage stack, you hear the word stack a lot, vent stack, drainage stack, very straightforward. The reason I like the commentary is they have a lot of diagrams. Again, I won't get into this. This is, I think we all know individual vent, pretty self-explanatory. It serves one trap. Again, venting by itself is all about allowing air into the system, air in and out, and to protect our traps. We need to keep these traps sealed, that's sealed with water, to prevent the, obviously the soil, the gases from coming out and getting into the occupied spaces. We use the term water column a lot. Well, this is definitely important in traps. You'll see a requirement that a trap has to be at least 2 inches in depth, and that's because you want to maintain at least a 1 inch of water column. So there, you really want to keep the two, a 1 inch water column, 1 inch of column of water in that trap. You really should be designed for 2 or more. They'll allow a pressure differential of 1 psi or 1 water column, 1 inch water column, so that that trap stays complete. Again, building sewer, circuit vent. We're going to get into detail about circuit venting. So the venting, again, the crazy part, we'll see if we get to, we got vent stacks, relief vents, fixture vents, individual vents, common vents, wet venting, waste stack vent, circuit vent, combination waste and vent, island venting, single stack venting, and air admittance valves. Oh boy. So there's probably, I always considered venting one of the trickier. To this day, I struggle with it, and I always go back to this book to try to say, hey, am I doing this correctly? Because there are many different ways to do it. Common vent's the one that we use just to serve 2 fixtures, 2 identical fixtures typically. Developed length, another important one to keep in mind. This comes into play anything over 40 feet. You have that vent line gets over 40 foot. Developed length, you have to increase by 1 pipe size. Now, again, in plumbing, you'll see developed length or equivalent length. Developed is just measured from point A to point B. You're not adding extra for the fittings like equivalent length. So keep that in mind. Again, that little distinction will come in the, you're doing gas pipe sizing, other sizing, whether you need equivalent or developed. Gonna get on to stacks again. This again, another one that I will probably misspeak during this little presentation. We got stacks. That's any vertical pipe, really. Soil stack, sewer stack, storm stack, vent stack. Stack vent is you got a waste stack, and then it keeps going up. That becomes a stack vent. But that's different from a stack venting. So stack vents, vent stacks, a lot of different stacks. There's the vent stack, which is kind of its own individual vent system. Again, drainage, I only put this in here, again, folks, we don't, venting relies on that we're venting a sanitary system. So the big thing here is, I think we're all, if you're not familiar with, you're definitely, your step 1 is developing your drainage fixture tables, as well as you would normally also get into your water fixture units, but drainage fixture units, the same drainage fixture units are used for venting as well. So you'll use these same tables. So you might want to have a handy, you can always look it up in a book or have your own little copies of the building drain sewers, how much you can do on an 1/8 inch line, how many fixture units based on the pipe diameter, sewer line we're talking about. And again, the nice thing about the commentary, they'll give a lot of examples. They're not always my favorite examples because, boy, they love themselves 3-inch waste pipe to water closets. And as a firm, we kind of default on 4-inch. So right off the bat, I'm usually not lining up with how they like to line up. Again, horizontal branches to stacks. So branches and stacks are looked at differently, which makes sense. Here's a little diagram. I think a lot of people have seen what's going on in a flow. When you got the pipe, you got your solids, your water, and then you got air. So that's why it's a combination. A horizontal, we're looking at half of that pipe is air and half of it's water solids. In the vertical, it's 7/24. I don't know, it's an unusual number. Basically, it means that 2/3 of that's air. So again, the venting, it comes into very importance with especially stacks. Think of that, all these branch intervals, all this drainage dropping down this line. When it hits that bottom, there's a lot of pressure that ends up being compressed air. So that's where you don't show it here, but there's typically a relief vent or vent stack that's associated to any stack of this height. Surprised they even showed up there. Finally, get to the venting. Trap seal protection, talked a little bit about that. Again, that's what we're doing. That's the primary goal. Keep the water in those traps. They got, again, good pictures of traps. So there's back siphonage, there's back pressure. This is actually back pressure. Back siphonage would, think of a line pulling, going fast velocity here, it might pull a negative pressure on this line and empty that. Again, that's where the 2-inch comes into play. Through generations, they determined that usually was enough to protect that trap. Vent terminals, we've had a lot of conversations, a lot of coordination, where they go. International code, I can't speak to the uniform, wants it 1 foot above the roof. You'll see some other requirements. Usually we don't have the same as like a fresh air intake. The key is the distances come into play quite often. The one that we all know is 10 foot from any fresh air intake. And those are minimums. It never hurts to be a little further. And windows, a little different criteria. And sometimes you got to be careful above and below and where that might be. But think about the further you can get those vents. And that's where you're going to have to be more flexible. It's easier to move a pipe than it is a mechanical intake unit. Vent extensions, again, just stuff. There's always one that goes to the outside per building. Air admittance valves have become popular, but you have to have at least one vent that exits the building. Vent stack required. The branch intervals, again, something that we'll touch on. Branch intervals is just really think of every floor, every story. It's only 8 foot. I don't know. I guess if you had a really tall space, you could have multiple branch intervals in the same floor, but that's more the exception. You also find a lot of information out here that they do a lot of discussion for high rise, and a lot of us don't have a lot of experience, maybe multifamily, or if you're in a larger city, you're doing bigger high rises. There's a few more rules you have to be careful of with how to handle these branch interval, multi-story buildings. Vent terminations, again, I can't go into every little note that I highlighted. Vent connections, that's one per building. Here's that, it's kind of a vent stacks where they're having coming off to help support that stack getting down at the bottom. So we're besides each one of these branch intervals will have their own individual vents. But when you get a stack of 5 or more, then you're going to have to add a extra, I'm calling it relief. They just call it a vent stack. And then there's 2 different methods, coming off the bottom, or you can come off the vertical portion if you have the space. They want it close to that last branch. Vertical rise, every dry vent should be vertical to a point at least 6 inches above the flood. This is kind of hopefully makes, and again, I can't go through every detail. Spend some time looking at their calcs. Again, these are going to reference back to, we'll talk a little bit about sizing a little bit. Again, drainage fixture units, and then for stacks, they'll have their own tables in the code. Otherwise, you're looking at most vents are sized at half the size of the required sewer pipe size, sanitary. The key to 6-inch rule is a good picture here. These are things that when I started in industry, we could do this. And this was particularly important with, you had runs out to floor drains or spaces where you didn't have walls. Say, how am I going to vent this? Well, you just came out the side and go find a wall and went up the wall. You can't do that. You have to come out above the floodplain. They let you go vertical or at 45s. And then once you see, if you got to 45, you still have to, before you went horizontal, it has to be 6 inches above the floodplain of the fixture. This is the best example. So I can't just go horizontally here and then go up. I can't have any horizontal vent. It's got to be above floodplain, which is the floor in this case. So these, again, there's a lot of good examples. This is the ideal way to think venting. throughout my history of doing plumbing, I've had to reroute sanitary to find walls. I don't say it's not the logical way for me to run that pipe, but I'm doing that to get to a point where I can do a vertical vent pipe. Very common. See, here's not acceptable. It's kind of neat that they put these not allowed. Here's a better example of, yeah, just get above. Another little rule of thumb, I like anytime I go vertical, I personally will almost always add a vent. So we could look into circuit venting and other, but this is not a horizontal tap, but there's lots of venting methods. There's no rule that says you can't vent every fixture. It just gets into economics. A lot of times though, vertically, it's best to just vent off each one of those. You can save your money by, I don't need to go, let's say this is at 2 foot above finished floor and my ceiling's at, 15 feet. I don't have to go each one of these up 15. I can take these, just go 6 inches above that, the rim of, in this case, probably the rim of the sink, and then take one line up high. So those are things to think about. You'll see that if you get a chance to go in the field and see how the plumbers are installed, they're going to try to save pipe, and you'll see them getting those, combining them at a lower elevation to save on pipe. Vent pipe sizing. Again, the minimum required diameter stack vents and vent stacks, there they got reverse, shall be determined from the developed length. And they tell you to look, the stacks, look at the table in the venting size. Never, diameter should be not be less than 1/2 of the diameter of the drain served, or never less than 1.25 inches. Vents other than, that was about vent stacks. So vents other than stacks or stack vents, a branch vent or individual vent. The diameter of individual branch vent, circuit vents, relief vents shall be not less than 1/2 the required diameter of the drain served. Now and then we go on here, talks, this is where that 40-foot rule. The vents exceeding 40 foot in developed length shall be increased 1 nominal pipe size. Frankly, I've done a lot of work where, to be safe, you'll be hard pressed to find 1.25 inch vent line on my work, and that's because I think it's rare that if I'm doing a 1-story building, then that developed length is really from that fixture all the way to the vent through roof. Now, if I have a vent stack, it's just to that vent stack. Again, it depends on how you're laying out your. If you have a multi-floor, then you probably have a vent stack somewhere. But so a lot of times, just safer to be that one pipe size, not 1 whole inch. So 1.25 becomes 1.5. But that could be, that's, if you need to squeeze every ounce of cost out of it, right size it. You can do 1.25 inches. The key that I've really kind of relearned is I've historically used 1/2 size of connected pipe. Here it does say required diameter, and I say that because his commentary shows examples where they might have they'll have 1.5 inches on a 3, where I'm saying I would run a 4-inch pipe to that water closet. Now, do I have to run a 2-inch vent, or can I use an 1.5 inches? By saying the required diameter, my understanding of the code saying, hey, if the required was only 3 inch, then half of that's 1.5 inches. Again, I'm not sure every code official will read it that way, but that's how they demonstrate it. I always did it based on the actual pipe I was connected to. I don't know if that makes sense. It might be in some of these other examples coming later. The sizing of vents, other than vent stacks and stack vents, is similar, blah, blah, blah. Again, they're referring back to chapter 7 tables in the sanitary. So again, that's that whole idea that it's related back to the sanitary sizing tables. I just threw this in there. I copied them in from the sanitary. These are the same ones. This example, again, if I had more time, we'd actually run through some examples, but if you don't have access to a commentary, work on getting it. It's so much better than just the plain code. I mean, that's true of HVAC and plumbing. They have a little explanation of what's going on and why it's going on. Technically, commentary is not code, but it's rare that you can't use that in dealing with a building official. again, no, this running through the examples helps give you an idea. Okay, they're telling you what the drainage fixture count is and develop length, and then you can go back to the tables that they provide. That's what I had these highlighted here. This is for stacked vents and vent stack. So it's, again, a stacked vent is some sewer line, sanitary line going up, and then it becomes a vent at the top. A vent stack is a vent by itself that's probably venting the lower building drain. But again, multiple 4-inch pipes, then you have to look at the drainage fixture units, and you have to go, in this case, I'm sure it was like, 440, I think it said. Well, then I got to look at this line, and I go across, and then if it was, if it was under, if developed length was only 40, then I could have done it with the 2.5, but I had to go up to a 3-inch line because it was somewhere between 50 and 150. So it's pretty straightforward and easy. So this is another one that maybe if you're doing a lot of it, you just print this one sheet off and keep it off to the side. Probably using a spreadsheet or one of your programs to keep track of your fixture units. This is some of that on sizing. This is where I was talking about where this is an example right here where they got a 4-inch line. They said 1.5. The only way that could be true, well, that's not half of the size. A water closet's fixture units would allow you to use a 3-inch line. So here's my example in the commentary. There are some commentaries I'm not crazy about, but again, multiple water closets and a 3-inch line, not my favorite, but that's, again, you are allowed to by code. And a lot of the plumbing code is based on, there's the science. If you look in the ASPE volumes, there are the calculations, but a lot of it's just historical testing and see just what was working, what wasn't working. So pretty much a pretty reliable source that this stuff has been vetted through just years of reviewing existing facilities and how they're working. Again, no, a lot of these, it's a shame they don't have examples. They rarely have examples where their developed length is over 40. So each one of these is telling me that these are the minimum sizes. Again, you just add up your fixture units, and then you would just like you would size the last 2 lines of the sanitary, you take those 2 and you just figure that back. I would add, they don't talk a lot about this, but I would say, what if for some reason this line was 4-inch and maybe some companies have a standard to have buried pipe larger, but yeah, a lavatory only needs 1.25 inches. Well, this line is not just venting this trap, it's protecting that trap. It's also venting the line that's serving it. So I'm saying that this might have to turn to a 2, and this would be, if this is 4 down here, I'd make this 2-inch. That's my take on this. Again, I should say it's oversized. So by code, they're saying no. If you only have this one drainage fixture unit, you could do an 1.25 inch line if it's under 40 feet. That's another example where it's by the required size, sanitary size, and not the actual size. Ultimately, what they're saying is you're replacing this much. When this gets drained, you got to replace that much water with air. So that's what ultimately you're changing this. If this line was feeding other places, if you were venting this line, pick one of the vents that's venting that line and make that the 2-inch. I kind of backtracked on myself there, but let's see what's next. This again, a lot of good examples and sizing. They love their 3-inch. Here they got examples, developed length, where they increase. Like here's one they did increase in size because it was the developed length added 35 here before it got to the vent stack. So we're really this is just one system. I consider that all the way out. So they went from 1.25 inches to 1.5 inches. So there's one they did upsize. They talk about, here's the example where they talk about this is the extra line. They're saying that the developed length is just to the vent stack and not, this one's an individual. There's no stack involved, so it's vented all the way to the outside. I again, I've always measured if this was 1-story building, I would have taken that to the vent through roof, but according to the code, it says it can stop at the vent stack. They call that a stack vent. Boy, there is a vertical waistline, so this does become a stack vent. So I guess that is appropriate. This is a better example of what I was talking about, where the vent developed length goes to the stack. They're saying it goes from this point V to W or X to W. Again, this X does cross through, so, but they're not including the stack. That's, you know, so you have to add, if this was an extra 30 feet up, you can basically ignore that 30 feet.
Hey, Brian,
Yes.
that is good stuff. We have just got to the 12:30 mark. So
Yeah.
I will ask if you could maybe finish
I'm
up
gonna
with a couple.
Yeah, I knew this was, I apologize. It's like, there's no way to do it, but give me 3 minutes. I just want to highlight vents stack off. Vents, don't worry about, you just be a vent stack. You can't offset certain elements. Be very careful about offsetting anything that has drains above and below. That's talking about stacks. I am. Common vents, it's just same fixtures. That's pretty standard. You can use one vent for both. Wet venting. So the wet venting, keep in mind, this is something done for bathroom groups. And so that's just use it within bathrooms. The idea is that you can see here, you got a lot of times for one bathroom group, you get one vent that's venting not only that last fixture, but also the other fixtures within that bathroom. The idea is that there's enough air, that there's a little oversize. There's a special table for doing that. Oversizes the pipe a little bit, and the air in that horizontal is enough to vent these lines as well. When you get another important one, trap distance to vent, there's a table for that. Be careful. The bigger the pipe, the further it can be. A 4-inch floor drain could be 16 feet. A 2-inch is, I think, what, 4 feet or something, so be careful. Again, look at your commentary, look at your code, and you'll see a lot of stuff. So wet venting, then we get into lots of stuff on wet venting, lots of rules. They talk about too many fixtures. You can't have anything more than, your fixtures should be the last fixture, one fixture downstream. You can't have other products going through this vent line. I can't have a kitchen sink passing through what is really considered the wet vent. Be careful. Nice if it's just limited to that bathroom. Lots of rules here. Again, a commentary points a lot of that out. What else I wanted to get? Vertical wet vent. I can't believe how much I have wet vent. Waste stack vent. Again, key word here is waste. So this is only good for anything. Can't put urinals or water closets. So, but a way that this vertical waste stack is also the vent. Saves you an extra vent line. Circuit venting, very common in the best picture is these gang bathrooms. We've seen the large ones. The idea of just having, you can do up to 8 fixtures off one vent. You go over 8, you just add an extra circuit vent or relief vent. And so up to 8, one vent, don't need them all. No crime if you got wall carriers, no crime in adding those little short runs. I think added vents, you won't have problems down the road. That's my opinion. Combination waste and vent. Again, here the key to the word is waste, being you can't have, this is another one, you can't have water cloud. They don't want solids or fecal matter in there. So again, it's another way to have less venting. They kind of, back to circuit venting, they overlap. They tend to be a little late with their diagrams. Got all these, they're saying all these floor drains off one vent. I don't know how they're, usually I would say I would tie these into that same line. The fact that you got 3 tied in before it goes back to the vented line is, I don't really agree with that. Again, all these are combination place vent, another great resource to reduce your venting, island venting, single stack vent. This is an opportunity to do, again, you see it in high rises, to do one stack that acts as a waste stack and vent stack, or sewer stack and vent stack to serve multiple fixtures. Usually they're just tapping right off that main line. You cannot do that. You can't do the lower 2 floors. So it really comes into practice. What they're saying here is, I could do floors 3 through 10 with that vent, but the first 2 have to be their own stack. Lots of weird little rules. And the more you get into it, again, go back and look at this and you will find great information. And remember to vent your grease traps.
Yep. That is
Sorry,
good.
that's
Yep. Good
all
resource.
share.
I know it's a big subject and we could talk a lot about it. So good resource. Y'all keep an eye out on your ASPE web pages to snag those documents. And with that, we will move on to Tom and go over storm drainage. So Tom, the floor is yours.
Well, good afternoon, everybody. Hopefully everybody can see the document that I just put up. This is Plumbing 101, so there's some things we aren't going to cover today that are kind of a little more specialized things like siphonic roof drains, gutter downspout systems, site drainage, controlled flow systems, under drain and foundation drains, and combined sanitary and storm drainage systems. We have some excellent information to use for designing these stormwater systems. The International Plumbing and Uniform Plumbing Codes, excuse me, and the associated commentaries are outstanding resources. ASPE's plumbing manual is terrific. You will get into times where if you do work in places like Wisconsin or in Canada, they have non-national plumbing codes, and those are a big gotcha. You got to be really careful on those because they can really pinch you when you don't expect it. So the way I go about doing a stormwater system is the first thing I try to do is try to collect information about the local area, local rainfall rates from the, for example, the IPC in section 1106 has a chart that shows what the rainfall rates are anticipated to be for that area for code compliance. I usually add a half an inch to those requirements. Our rainstorms, and our civil engineers have noticed this too, our rainstorms seem to be higher intensity when they happen. And that little bit of oversizing a roof drain system doesn't hurt. And I've never had anybody express concern about the cost of it. Sometimes you won't notice a pipe size difference. Sometimes it'll be a minor difference. So there's a lot of different kinds of roof drains out there. There's traditional roof drains. There's scupper drains that go into the sidewall of either buildings or canopies, things like that. There's combination drains that have both the standard roof drain and the overflow roof drain in the same package. So they're easier to flash. They go in more quickly. They can be really nice to use. And we usually depend on our architectural and structural friends to locate our roof drains for us. One of the things that we have to look out for if they don't think it through is what kind of drop there's going to be across a roof. Sloping the structure makes it a little bit easier, but if you have a roof that has tapered insulation, trying to get between 1/8 and 1/4 inch of slope across the tapered insulation can lead to some pretty big slopes and some pretty thick insulation sometimes. Roof overflow drainage is also covered in the plumbing codes, and the roof drains, there's different philosophies on how to do it. One is to put the roof drains together and put a dam on the overflow roof drain. Another thought is to put the roof drain separated by 10 or 15 feet. But we really need to work with our structural friends on that to see what kind of loading that they can bear. And another thing I like to do is I like to work very closely with our civil engineers on where our drainage points are going to be on site. So we can pick up what elevations they're going to be at, where their locations are going to be, what kind of capacities they have, and how they're doing their system. If they're doing part of their system to some swales, other parts of their system to bigger areas, That's really helpful information, and you can avoid a lot of rework if you work closely with your civil engineers when you do that. Sizing the drainage system. International Plumbing Code uses GPM for capacities for roof drains and piping sizing. That's handy for piping sizing. Roof drains, I typically have been specifying roof drains by the GPM they need to have as capacity, and then checking that during the shop drawing phase. And that kind of provides a little bit of belt and suspenders information. I also like to show the GPMs I use when I design on the drawings, and that leads it to be easier if I have to make some adjustments if roof drain locations and things change over time. So one thing that's a gotcha that not a lot of inspectors will pick up on necessarily is you have to compensate for vertical walls adjacent to flat roof areas. And most codes, including the International Code, look at picking up 50% of that vertical wall area that's adjacent to a drained flat roof area as extra size and capacity. And sometimes that can add up really quickly if you have a school with a gym with a tall vertical wall. That can add up very quickly on your roof drain sizing. So once I have talked with my civil engineering friends and my architectural friends, and I have my roof drain locations and my discharge points, what I tend to do is I tend to take a look and kind of connect the dots above ground and then below ground, and work out my best routings and things like that. I try to, when I lay things out, I try to immediately do my clean outs when I do that. And there's some gotchas and clean outs too, like the 2018 Michigan Plumbing Code requires manholes in lieu of clean outs if your underground storm sewer piping size is over 10-inch. And that can be not attractive in some buildings. If you're doing a warehouse, it's not necessarily that big of a deal. But if you're doing an office building or a finished area, having a manhole in there is not very attractive. And then the overflow system, I usually track that at the same time. And the overflow system is sized very similar to the main system. You look at the vertical walls, you look at the areas drained and the GPM, and the code verbiage in the International Code is it has to discharge to a location that would normally be observed by the building occupants or maintenance personnel. That can be up to interpretation by local code authorities. Most inspectors are fine with taking your overflow drain system and dumping it out above grade where you can see it. We've also done buildings where we dump it out like through a canopy, just straight through the canopy, so it just drains straight down. We've also done some buildings where our stormwater overflow discharge is high on the building, so you don't have an extra length of pipe dropping down and discharging out low. That's up to personal preference, what the client wants to see and what the inspector will accept. Most inspectors are pretty good about that. Another way to approach this is you don't excuse me, you don't need an overflow system if you don't have anything that impedes the water from going over the side of the building, and your sloping is such that your structure will hold it. We've done buildings with gravel stops on the edge, and it'll build up maybe 4 or 5 inches, and the structural engineer knows it ahead of time, can make sure that the structure is designed for that, and that eliminates your stormwater overflow system, which can be not an insignificant amount of money saved, and also piping that can be intrusive sometimes if you have finished spaces you're going through. So piping system design considerations. One of the things that I do is I like to take a close look at the space this is going into. For cost, most people like to use PVC piping, which is a great system. But there's some municipalities like the city of Chicago that do not allow any plastic piping of any sort in any situation. And PVC is out, so cast iron typically is in. Copper and stainless steel are also other materials that you don't see very often. The ASPE guidebook has an excellent section, and there's also some really outstanding read, earn, learn sections that talk about sound and plumbing systems. And so a lot of that has to do with stormwater drainage systems. You can stack it up by doing cast iron instead of PVC, which mutes the sound. Also insulating the piping and using an acoustical insulation instead of just a thermal insulation. And another method of doing that is boxing it in and adding extra acoustical insulation with a couple of layers of drywall below it or around it. And ASPE has their Read, Earn, Learn has an outstanding discussion about acoustics in plumbing systems, and that's something to really look out for. I tend to insulate storm drainage systems from roof drain body to the underground system, just because I know that some people who don't do the vertical systems, you can have vertical piping sweating, and it's less common, but it can still be there. And this way you eliminate the possibility of doing that with a decently insulated system. So one of the other gotchas is sometimes it would be convenient to run, for instance, off a small roof, a drain, and then reduce the size vertically when you're going down, but you can't do that in the Michigan Plumbing Code and the International Plumbing Code because of Section 704.2. You can't reduce the size of the piping downstream, even if you don't need the size for capacity. One other gotcha is I had gone to a seminar, and a gentleman who had done service work before he got into the inspections was talking about cleanouts and how they work. And he told about a time when he was doing service work when he was a young plumber, and he was in a warehouse type building, and there was this 8-inch stormwater line that was backed up on the roof, and the water was coming out of the overflow. And he had a pipe wrench on the base of the stack clean out and almost opened it up before he started to think maybe a roof with 5-6 inches of water on it with an 8-inch storm line and opening it up might not be the best idea. And he said, if I had done that, I would have flooded the store. So his take from that is more cleanouts are better, and be careful what you open up and where. So that's what I have for stormwater piping. It's a relatively fun system to design. Like I say, it's kind of a connect the dot type system, and playing back and forth and using some forethought a lot of times can eliminate having to rework things if there's minor changes on the roof. There are some gotchas, and like the vertical walls next to a flat drain roof, that if you watch out for those, you can usually keep yourself out of pretty good trouble. And again, I'm recommending going to the ASPE Plumbing Systems Manual, Volume 2, Chapter 4. It's got some excellent information. And also, not only can you get some CEUs by doing the Read, Earn, Learns, but there's also some outstanding information in there about how to design systems and on subjects like acoustics in plumbing systems. So that's all I have for today. So thank you, everybody.
Yeah, that's great, Tom. Thank you very much. We are about 10 minutes shy of our next presentation. We certainly can jump into that. Would there be any questions from anybody? I'll probably give a few minutes maybe just to see if anyone has any thoughts. So feel free to give them in the chat or unmute your mic.
Could you put some of these resources that you've mentioned in the chat?
I can put my outline in there. Yes.
I was thinking more of, you said the read, earn, learn, and what specifically are you
Yes, I can put
referencing?
a link. I can put a link into that.
Perfect, thanks.
Yeah, those read, earn and learns, those are great resources. They come from people in the industry from across America, so they're free downloads. So keep an eye on that.
Yeah, I'll add quickly, Tom and I, well, this whole group is being sponsored through ASPE, and they are probably the #1 resource for all plumbing engineering items. If you're not a member, one of the advantages of being a member is you do get the access to their main 4 volumes of books that cover just about anything in the field, from your basics sanitary to med gas to whatever. They do tend to, they're not tied to one building code, so you got to be a little bit careful. I'll just tell you that. Storm's another one where I was just doing some work down in Texas, and it's straight. This is had to use 8-inch per hour. That was quite a lot of rain, and and it was strictly, this area of roof, and this is what pipe size you'll use. Very straightforward, but it's different. So then you go to ASPE, and they're trying to balance between international and IAPA and uniform. So, but it's still very good resources. And you just go to their website, and you're pretty well set up to find educational information. And they even have online videos that you can get CEUs. So if you're ever looking for CEUs, you can check that out as well.
Yeah, that's a great question. Does anybody else have any questions before we move on? Okay, that's fantastic. We've got Jonathon Rumohr presenting next on domestic cold water, and so we're looking forward to that. So thank you, Brian. Thank you, Tom. And John, the floor is yours.
Great. Thanks, Luke. Appreciate it. Thanks, everybody,
Yeah.
for joining today over the lunch hour. Hopefully, I won't hold you too much past the lunch hour. Kind of talking with Luke a little bit about how we wanted to format our presentation, going through kind of an early conceptual design level on how to size a domestic water system, specifically the cold water side of the domestic water system for your project, and what are the steps with that, and how is that impacted by the current plumbing code, specifically here in Michigan. So with that, I'll go ahead and share. Get rolling. So going through and sizing a domestic cold water system is pretty straightforward overall, but the couple of gotchas that we can go on along the way. Couple of main steps that are broken down into 5 main pieces for everybody to keep aware of as you're going through and sizing your domestic water system for your building. First off is know your site conditions, right? Once you know your site conditions, most municipalities go ahead and deliver water to the site between 50 and 80 PSI, but that could vary based on your specific site location, based on site elevation, based on what the municipality has, whether or not it's, is the municipality on well, is it on tower, is it all a pumped system? So depending on where you're at, you could vary quite a bit in your overall pressure, which will then impact your overall sizing and your need throughout your building. So that'd be step 1, knowing what available pressure you have available at your site. Your step 2 is gather up all of your fixtures that you have in your building and your project site and determine your water supply fixture units based on the fixtures that you've got selected for your project. Doing that, you look at the local plumbing code for the sizing criteria. Here in Michigan, as of March 12th of this year, Michigan is on the 2021 International Plumbing Code, or IPC 2021. And Appendix E, which we'll get into in here in a little bit, defines those two different sizing methods that we can take a look at on how to develop that overall sizing criteria. But first step with that, going through and putting together a table of all of your fixtures. I've gathered up pretty typical ones here that we'd be taking a look at, starting with lavatories, urinals, water closets, whether or not those are tank type or flushometer type. If you're doing private or multifamily work, bathtubs, service sinks, kitchen sinks, and shower heads. So a little example that I've got here of a little 3-story building. I've got a handful of lavs, a handful of urinals, and a handful of water closets. All the water closets and urinals are flush valves on this. This is a little 3-story building, and we'll go through and kind of run through this as an overall example. So adding all of this up, we come down to having, 9 lavatories, 9 urinals, and 12 water closets, which overall gives us a total water fixture units for this example facility of being about 178 water supply fixture units, as here. And then going to Appendix E, the plumbing code, we can look at those 2 different methods that I'd mentioned earlier. E103 being a segmented loss method where you are calculating the individual pipe loss or friction loss through every segment of pipe in the system. And then section E104, which calculates based on the developed length of the entire system. In my experience and in my career, I've typically used the developed length method in lieu of segmented loss, mainly due to overall ease and efficiency in putting together our sizing for our system. So going back to our overall example, if we add all that up, that 178 fixture units that I mentioned earlier, if we're a 3-story building at approximately 35 feet tall and an 85-foot length and then a 5-foot drop in the wall, we're about at 140 feet of length, total developed length from our meter. We would want to add a factor of safety on that to account for pressure drop through fittings. The section E104 of the IPC 2021 calls out 1.2. I've typically used 1.5 as a fitting factor of safety, which gives us a total of 210 feet to the most remote fixture in this system. So 100 feet, as I mentioned here, 140 total feet, and the 1.2 per E104 or 1.5 for that greater factor of safety gets us to that 210 total feet. And then we can go back for the developed length method back to E104.1, which gives us a series of tables based on pressure. And if we have an incoming pressure from the street that we know at 50 to 60 PSI and our maximum developed length, which we were between 200 and 250 maximum developed length, and 178 fixture units, which would be between our 1.5 inch and 2 inch line size. So therefore, following this table, we would be going back to a 2 inch main distribution with for the 2021 IPC. And this just kind of goes back and shows that again. If we go back and look at an individual branch, say that 3rd floor run where we've got 159.5 fixture units or 60 and an 85-foot run or a 90-foot run to that most remote fixture, and go through and do the same thing for sizing the branches, that goes down, taking our head loss from being 30 foot up in the air now and drops us down to that 30 to 40 PSI range and between 80 and 100 maximum developed feet of length, and our between 60 and 70 water supply fixture units gets us down to an 1.25 inch main that would be running across that 3rd floor to feed those fixtures. The last step that we've got to go in there now that we've gone and sized our piping and sized our mains through it is to go and verify your pressure drop to make sure that your most remote fixture, and that could be may not be the most remote fixture from the meter. It may be the most hydraulically demanding remote fixture, in this case being a flush valve, to determine whether or not you have adequate pressure at your furthest fixture from the meter. So going back to the Michigan Plumbing Code, Table 604, if you go ahead and look that up, that will give you your code required pressure at each type of fixture. Our most demanding fixture being a blowout type closet, which requires 45 pounds to be able to operate that valve, or a siphonic water closet, which requires 35 pounds to operate that valve. Now, these can all change slightly based on manufacturer. This is just following the code recommended pressure at each one. So on your site-specific applications, go through and review that, whether or not you're a Sloan valve, you're a piston or a diaphragm flush valve, and those will change slightly and can impact your design. But if you're following it strictly based on the code, Table 604.3 is your spot to go to double check that. And then verifying your pressure drop across the entire system, you can add that up, put that in a table, going across your water supply fixture units. What is your minimum pressure available from the city? As we mentioned before, taking pressure losses due to height, going through your meter, backflow preventer, PRV if you have one, if for some reason you have a water supply pressure from the city at over 80 PSI. At that point, you would need a PRV on your system. And from there, being able to determine what is your total friction loss in the system. And a lot of times when you're at your schematic design or early concept design, you can bypass a little bit of this and use a little bit of a rule of thumb that I've been working with over the course of my career, of generally looking at a 3 PSI per 100 foot of lineal foot for branch pressure drop, or 5 PSI for the main. If you go back and run through that calculation example that I just showed, you can see that at this example, we're at 4.7 PSI per 100 foot of piping. And if you go back to the code and check our initial sizing on that 178 water supply fixture units, you'll see that both 3 PSI per 100 and 5 PSI per 100 both still result in us having a 2-inch main size for this building. So that's where we're at today. I know that was a little bit of a quick review overall, but give everybody a chance for questions.
Yeah, that's great. So I know I've got a question, but I personally will let anybody else go. I'm sure that's great information to maybe put in the chat if you're willing, kind of like Kim asked on the previous one. But does anyone have any questions?
Hey, John, I have a question.
Yeah.
Curious, what kind of buffer or safety do you like at the end when you're calculating your pressures between this is what your system design, this is what your fixture you think needs, say 35, and how much extra do you want?
Yep. Usually as a factor of safety at the end, I'll try to shoot for between 5 and 10 PSI. That'll help for over the life of the building for any occlusion or sediment buildup in the piping that'll happen over the building's life.
Thank you.
Anyone else have any questions? Shoot one off. I'm a little bit curious about wells when you're working in a remote, maybe a remote project where you don't have access to the city. Who is going to determine the pressure from the well? Is there a specific installer or civil or structural that, probably not structural, but someone that can tell you PSI from a well at a remote location?
Yep. So very similarly, we would be working with a civil engineering consultant when we're working on a well project. Very similar approach to this. We would be saying that, working with our civil engineer saying, hey, I want 50 PSI at the building to be able to get what I need to do. There's a little bit of difference in some of the pressure drop calculations, only because, you're not going to necessarily have a meter in your mechanical room. So you've got some pressure drop that's not going to be present in the system, but you would kind of do the exact same thing where you would still do your water supply fixture unit calculations and work backwards from there to get a demand pressure that you would then be supplying back to your civil engineer or your well designer to get that for you.
Okay, fantastic. Thank you. Would you be able to maybe drop that presentation in the chat or maybe drop some snips of it?
Absolutely. I'm happy to share.
Yeah. Well, that is fantastic. That probably is going to conclude our AYP event, and we're able to probably sneak out of here a little bit prior to 1:30. This is recorded, so once we get CEUs figured out, we could send this recording as well. Brian, from an ASPE board perspective, do either one of you have anything to add to this presentation and this time together that I've missed?
No, I think just thank you everyone for attending. Thank you, John and Tom, for giving wonderful presentations. These are kind of broad brush reviews. There's, I think, with a lot of talk to your senior engineers. There's a lot of tools out there to make our life easier. But it doesn't hurt to understand what's behind each of those tools. So just rely on, here I got a spreadsheet, so I'm gonna be able to do this plumbing. So the more that you can understand what the system's doing and why it's doing it, you're a better engineer.
And also to add to that, on the stormwater and the domestic water sides, talk with your civil engineers too. Get your fire water pressure reports from the municipalities, things like that. It's almost like detective work a lot of times, and working with them closely can really give a lot of good benefits for us and for them. So,
and I'll add, if you don't like your civil engineers or structural people, then you can just focus on venting. That's the one that I rarely discuss with other trades, other than, they're going to frown if I ask them to drill a hole in a beam to put a vent through it. Venting is, you can usually work around things. Can't trap it. Don't put a line and drop it. Remember, folks, that's water gets in there and it needs to get back to the sewer. So we don't talk about sloping of vent lines, but there's another little vent tidbit. But you don't worry about the civil when you're venting.
Okay, that's fantastic. Nick Von Meyer, he is our board member that will be handling CEUs. His email is in the chat. So go ahead and grab that before we jump off. nickv@gmb.com. You could also email any of us if you don't snag his email, but I think that's it for our time together. Any closing thoughts?
Luke, I'll put one more out there. We got people send in emails to Luke or anyone on your board if there's something else that you think would be of value down the road next year. It's probably a good idea if we do this yearly and just a different topic. So if there's a topic out there that's been frustrating you or you just want to learn a little more, let us know and we could try to prepare something.
Yep, and that's a great way into another topic. This year, we are going to plan an AYP event, and it is going to look like a site. Maybe I shouldn't say site visit. Probably a facility tour would be the correct definition, but there's some discussions about some facility tours in our area. It will probably be in the Kalamazoo area, so keep an eye out for that in the next couple of months, and we'll go and look at some really cool, fancy engineering, and it might just be something that Brian or Tom or John designed, and we get to maybe see the ins and out of that. But there's some facilities around the area that we've got good connections with, so some great opportunities to get in the guts of a building and see some things. So keep an eye out for that.
To go back to bells, I'll certainly be there.
Okay, well, with that, thank you, everyone. We'll conclude this presentation, and I appreciate all the presenters. Thank you guys, and everyone have a great day.
Thank you.
Thanks, Luke.
Thank you.
Bye-bye.